So we did our initial analysis, we got that curve, we know that the survival times here that we see is not normally distributed. And also, we found the variances for the two samples. Variance of A was pretty large. Just because the number is larger in magnitude doesn't mean that it is incorrect. That value is large because all of our observations had, or a good amount of them, had large values. And same with the second one. Variances clearly are not equal. So another violation of assumptions: one, not normally distributed; two, variances are not equal. Yes.
It's not normally distributed because the green one is like shooting really high up in the blue.
No, neither of them look like a bell curve.
Okay.
Right? I want them to look like a bell curve. So I'll put the violations here. Now, here's the question. What if one of them is normally distributed and the other one is not? Could we simply use the test result and move on? Paul says no. The correct answer is no. Both samples need to be normally distributed. So even if one of them is normal, if the other is not, we still cannot use it. So we have unequal variances, but that is not an assumption. That just helps us identify the test. So I'll put it as case. Yes.
It's in the notes that the variance can be close to each other. You use the approximation symbol for the variances.
If they are.
Yeah, so how close do they have to be?
That's a good question. Someone else asked that question last time. How close should they be? We have a test for that too. But we will see. I don't want to spend too much time on this test, but in practice, oftentimes we're not going to encounter an equal variance. Always going to be unequal or more likely. So we simply go for the Welch's t-test. Good. Okay, that's it. We have violated assumptions, but still I'm going to push through and do the same command from last time, p.test. I have two samples, one from treatment A, the other is from treatment B. These are survival times after giving the drug. Now you can tell me what type of test we want to do based on that picture. Should we do a right tail test, a left tail test, a two tail test? Phoebe says right. Is she right? Rob's not. I reject your null hypothesis. Sure, I can do a right tail test, but it seems like there is an overlap. One may actually ask, well, perhaps they are one and the same. Yes, a two tails would be a good choice. Is there something wrong in doing a right tail test? Absolutely not.
I have a question.
Yes.
So are you not going to normalize it?
Answer what, Phoebe? What do you mean?
Like, are you not going to like make the graphs normal?
We can. There are ways to do it. I'll talk about that later.
Just keep going.
We're just going to keep on going, and then I'll make a note that it's not reliable at this moment. when we did dependent t-test, I used a very specific command. What is that command?
What'd you say?
I used a very specific command in the function. This is for math majors. I'll give you a hint. It's right there. When we did the dependent t-test, the dependent case, we used part equals true. That would mean we have a part comparison. By default, it is set to false. So if you don't specify anything, it is going to do a two-sample test. The next option there, var dot equal, is going to determine whether we are going to do a Welch's test or a regular two-sample test. I'm going to do the first case where I'm going to assume variances are equal. Am I making the right assumption? Excuse me, correct deduction here? No, I'm not. But the reason why I'm doing it is to show you what the results would be like. So our objective is to determine if mu1 is equal to mu2. Average survival time for treatment 1 is equal to the average survival time of treatment 2. What is the alternative? If the null is that they are equal, the alternative will be easy question and not equal. We'll call this M1 or mu1 or mu A, mu B. Here comes the important part. Now that we have the result, you can tell me, are they the same or are they different? By looking at the picture, last time, if you remember, we said, oh, there's a lot of overlap between the two. So it's very likely they are the same, the average survival time. Now that I performed the test, look at the test results, and you can tell me if the average survival time for treatment A is the same as the average survival time for treatment B. No, why not? Where's the sound coming from?
Last one.
Okay, so Nikki looked at the last line. Should I make my entire base my entire conclusion using the last line? Entirely. Oh, no. Why not? That would defeat the purpose of statistics, right? All The last line is simply giving us the average survival time for treatment A, average survival time for treatment B. It does not answer the question whether they are statistically the same or not. So, anything else? There are two ways to come to a conclusion. Phoebe says the confidence is great, but how?
I'm really different. So I'm gonna see, that means that they're not. Say it. They're far apart.
The confidence interval does not contain zero. In other words, the 95% chance if I kept on repeating the study, 95% of the time zero is not going to fall in that interval. If that is the case, it's more likely that the average survival time of treatment A will not be equal to the average survival time of treatment B. Agreed? What is another way? Samantha?
P-value?
Very good. The p-value. The p-value is 0.0054. Great. How would we interpret the p-value?
Less than 0.05.
It is less than 0.25. What is 0.25? The significance level. Great. If we have to put it in words a bit more, how would we do it? What does that number mean to you?
Type 1.
Hey, type 1 probability, or
No.
you were getting close and then you went far away.
Actually,
It is not just type 1 probability. You are missing one word, Phoebe, one word. Starts with the letter E, ends with the letter R, 5-letter word.
error.
Error. Okay, so few things. In terms of inference, confidence interval does not contain zero.
Let's reject all.
So it is not likely that they would be the same. Number two, minimum value at which we can reject null, but we reject the null is 0.00054. That is our p-value. And that p-value is less than alpha. So the estimated type 1 error based on the data. This is an informal way of interpreting the p-value. Do keep that in mind. Line number 43, what I wrote is formal. The next line is informal. Do we agree that that is a very small probability? Oh, I put an extra zero, my bad. Well, that is an easy question. Do we agree that it is a small probability? Yes. So that is a 5 in 1,000 chance that you will be making a type 1 error based on the data. Again, line number 44 is an informal way to understand p-value, but it would make better sense. When we first started, our alpha was 0.05. We said we would reject the null if the p-value is 0.25 to begin with. But according to the data is telling us we don't have to start at 0.25. It's at 0.005. 4. So reject the null conclusion that they're not equal. I hate copy and copy paste, but I'm going to do it because we want to save time. The same test, this time I'm going to use variance equal to be false. That is something that we identified, that the variances are not the same. So I'm going to switch that to false. And obviously, we shouldn't get the same answer. We will see. Go ahead, Phoebe.
We used the variance of the word equal.
First case, I used equal, now false.
Got it. Hey, how are your cats doing? They're kind of old, so I just need to check it.
What it is. So this is a case where we repeated, but this time variance not equal, and automatically, if you look at the head, plays Welsh. And over here, the p value didn't change much, correct? And the confidence interval did change from last time. Oh, by a tiny amount. Yes. Not a huge difference, but it did change. Another change was right here. That's 119, 117.71. And someone tell me what? I did mention this last time. What is the formula for degrees of freedom in general for a two-sample t-test? N1 plus N2 minus 2. That would be 119. But I'm getting a decimal value, 117.71.
Oh, so you did something like an R, they use a different formula, so you did it up.
Exactly. So there is a way to come up with the degrees of freedom for the Welsh two-sample test. I'm not going to get into that formula. It's pretty huge, but because of that formula, you are going to get a decimal value. So regular two-sample test, N1 plus N2 minus 2, there you have to use the formula. Good.
Yeah. So basically, you could have used either one and got the same result.
I'm glad you brought it up. So read my mind. Basically, I could have used either one and come to the same conclusion. Agree? Don't see much of a difference. Yes, maybe. Which one would you pick?
I would pick Welsh's only because the variances are equal,
Okay,
just in case.
just in case, or is it the right thing to do?
Well, it's the right thing to do.
Just in case. It is not just in case, it is the right thing to do because the variances are not the same. So even though the conclusion did not change much, the interval did not change much, the right thing to do is to go with that. Good. But as we discussed earlier, put that comment here. Good. Regardless. Our conclusions are unreliable. Reason being, because Aaron, the data are not
You know, I thought about that.
normally distributed. So let's say you work for a pharmaceutical company and you identified that the variances are unequal, you do that part, you do a red test, give all the conclusions, but you fail to realize that they're not normally distributed. Whatever you did is wrong. Good? We don't want to make that mistake. Now, what do we do if we encounter a scenario of this sort? One, there is something called transformation. We can do transformations. Two, we just get a new sample. Right? In our case, this part perhaps is happening because of outliers. So I believe we did this last time. We compare treatment A and treatment B, and we see a bunch of outliers here, bunch of outliers there. Yes, before we even get into transformations, which I don't want to do today, that number is probably 1750 approximately. Yes, so I'm going to keep values below 1750 for sample A. And get rid of all of those and keep below 1400. So I'm getting rid of some observations that don't want them. So
Not working random.
come again.
Wouldn't you not be working randomly at that point then?
Good question. When we say randomness, randomness is based on collecting observations. This box plot, when it gives you these outliers, there is a rule to determine that these are outliers. So in 2023, you might have learned IQR. Do we remember? No? Okay. So IQR rule. So these outliers are determined using one of those rules. So just by looking at it, I can see that these numbers don't fit the profile. So I can get rid of them. Another way. Back to the other plot. Looking at these charts or density curves, the probability of seeing numbers past 1500 very small, right? So I can get rid of that. So are we introducing a tiny bit of bias? Yes, there are ways to fix that, but I'm showing you one of many cases. So I'm going to stop here for both samples. Good. Let's pick 1250 and keep only values where survival times are less than 1250.
TJ,
Yes,
I'm gonna make funny.
no,
Wait, let me tell you. So,
no.
wait, no, it has to do.
I'm not removing 1500 and above for sample 1, 1200 and above for sample 2. I'm going to chop off both at 1200. So let's say if I remove outliers, I end up getting somewhat normal of data. So that is my cursor. There. Okay. So placing a condition that the survival time for the first sample is less than or equal to 1200, and the survival time for the second sample is also less than or equal to 1200. This is a bit biased. However, I'm not introducing too much bias. If I pick that at 1200 and the second value at 2500, that's cool, right? What is that? Absolutely. Ah. I thought of subsetting, but we created a vector, so there is the first one. So the first sample, I removed values that exceeded 1200. If you look at the numbers, they're all below 1200. Going to repeat the same with the second one. If the violation is still there, we just have to abort mission. Again, treatment B, I've got rid of all observations that are greater than 1200. So those are the values that I have. I'm going to first check for variance. Variance of the first sample, 83,572.6. Variance of the second sample, 63,586. Relatively close compared to what we have earlier, right? Before removal of outliers. So even this is the case, I don't want to chance it. I'm simply going to go for variance unequal. That is standard procedure. So yes.
How far apart can these two still?
Going back to Aaron, question earlier, there is a test to determine how far we can go in terms of variances. I'm not going to do that in this class. So we don't have to be subjective in coming to the conclusion as to whether variances are equal or not. There is a test for that. But what I'm saying is, in practice, people will simply go for, it's more accurate regardless. So let's see. Do we want to do a histogram or density curve? Entirely up to you. Density, okay. Today, you get to know the difference between teal and turquoise,
No, where, oh,
if I remember. I think that is the correct code. Now that is teal. No, it's not. I beg to differ.
wait, what is that one? Teal?
That's teal.
Ew, I don't like it.
I don't need your opinion, Phoebe.
Wait, I thought. Wait, do you like turquoise better or teal?
Teal.
Oh.
But I like turquoise too.
Yikes. I mean, honestly, turquoise is cute.
I like both of them, but teal is more soothing than turquoise. It's like bright. Okay, now we did all that work removing outliers and stuff. Did it help?
No.
No. Would we consider this to be normal?
No.
No, by all means, it looks like it is bimodal. There are two different groups. One last way to test for normality, because someone might argue, well, you're looking at this picture and coming up with these conclusions, aren't they subjective?
Only 4 hashtags.
Thank you.
I don't think for them to all be the same.
Me too. We did Shapiro-Wilk test, which is a test for normality. I could have done this with the previous case also. I'm going to plug in the data after the one that we have after we remove the outliers, which is that one for treatment A. The null for Shapiro-Wilk's data is normal. We'll take a guess. What is the alternative?
Not.
Very good. Data is not normal. Something is better than nothing. So after removing the outliers. I got this answer. P value 0.0231, which would imply, should you reject the null, or which would imply the conclusion that the null has to be blank. You can fill in the blank, reject, not reject.
Don't reject.
Do not reject. Why is that, Phoebe?
Because it's bigger. Oh wait, it's not bigger. So reject the null.
We are going to reject the null, and we conclude that the data is not normal. What about the second one?
Wait, what is that?
This is called the second treatment, second sample. After we remove the outliers, the p value is extremely.
Paul,
So Paul should know.
Violate assumption. Well, it should just all the results, they're not trustworthy results.
Years later.
I'll be on the spot, they gave you.
Okay, go ahead, Paul.
Well, then the results aren't trustworthy. The results are not trustworthy.
That is true. Now that we know that the violations, the assumptions are violated, and we can't use a wedge test, is that it? Should we just give up, or is there an alternative?
I'm sure there's an alternative.
And specifically, Cleo and Paul should know, but they are disappointing me at this time.
I gave the answer. Someone.
I should get a pass today.
True, I'll let you go. It's your birthday.
So there's my pass.
Oh,
You're
Okay, I'll give you a hint. It has something to do with non-grammatic inference. So what is the purpose of non-grammatic inference?
Well, I've ever used non-normal distributions and small sample sizes.
Very good. All remembered.